Let's spend a few minutes looking at slope fields, which are graphical solutions to differential equations. Let's look at this differential equation, dy dx equals x plus 1. It's a differential equation simply because it contains a derivative. And unlike equations that you're used to solving, differential equations have families of solutions. In other words, there's a family of curves that have a derivative of x plus 1. And as you can anticipate, that family will be parabolas, vertical shifts of one another. Let's see if we can get a picture of that family of solutions. And we'll do that using a slope field. We're going to take some dot paper, and at every dot on this paper, there's an x-coordinate and a y-coordinate, and we're going to use that information to figure out the slope, and then we're going to plot that at that point as a little segment of that slope. So let's start at the origin. At the origin, the x-coordinate is 0, so the slope there will be 0 plus 1, which is 1. So I'm going to plot a slope of 1 at the origin. And if we move our way north, here and here and here, the x values are still 0, so our slopes will still be 1. So I'm going to draw slopes of 1 all the way up and also all the way down. Now let's move over to the next column, to the left. And in this column, all the x values are -1, which means all the slopes will be 0. So I'm going to draw segments of 0. And notice here I'm not getting too hung up on the precision of my slopes. I'm just trying to get a quick visual image. Now let's go to the next column. Here all the x values are -2, so all the slopes are -2 plus 1, which is -1. So slopes of -1. And we'll do this maybe in one more column to the left, where the slopes are all -2 now, because the x-coordinates are -3. And then maybe I'll do one more off to the right. Here, when x equals 1, all the slopes are 2. So I'm drawing slopes of 2. Now I want to make a couple of comments on slope fields. First of all, we've drawn a sampling of slopes. That's at a few points. But you should recognize that there's an infinite number of points that still reside in here. And we can't draw them slopes at every one of them. So we've drawn a sample of slopes. Also, we've given our segments some actual visible length, but in theory they should be infinitely small. So just a couple of caveats to keep in mind when you're drawing your slope fields. All right, now I think we have enough of an image here to see the solutions. And if you squint your eyes and let these segments sort of run together, you might envision parabolas flowing through these slopes. And that family of parabolas represents the solution to this differential equation. And we can see that family algebraically by taking our differential equation and rewriting it and integrating it. And the way to rewrite it is first to separate the variables. So what I've done is I've taken my differential equation, brought the dy dx up to the right, and now where I used to have x's and y's mixed together, I just have y's on the left and then x's on the right. So I've separated the variables. And now we can integrate. So I'm going to integrate the left and integrate the right. And integrating the right should feel familiar to you. You've seen this enough now that we can integrate that pretty quickly. And when you integrate the right, the integral of x is 1/2 x squared. The integral of 1 is x. And then we get a constant possibly. Now, integrating the left will feel a little bit strange until you recognize that you're just integrating using the letter y instead of the letter x. And what we're actually integrating here is 1, because there's a 1 in front of dy. And when you integrate 1, you get y. And you get possibly a constant, but our constant here on the right will capture both of those constants, the one over here as well as the one here. So C1 represents our combined constant. All right, we now have a family of solutions. This equation here represents the family of solutions, family of parabolas that go through this slope field. If we want a particular solution at a particular point, we can identify that point that we want, and I'm just going to pick an arbitrary point, say 0, 1. Suppose I want to get the particular curve that goes through that point. Well, I can draw it first by just moving through the slope field. And when you move through a slope field, you try to obey or honor the slopes in that slope field. It's not going to be very precise, but it should give you a nice visual of how the curve looks. Alright, so now we're going to take that point 0, 1 and we'll attack it algebraically as well. So I'll do that by putting in the point 0, 1 into this equation, and I get 1 equals 0 plus 0 plus C1. So C1 must equal 1, so my particular solution is y equals 1/2 x squared plus x plus 1. And that is precisely the equation of this parabola. Let's look now at another differential equation, dy dx equals y. So in this case, the slopes depend on y, in other words, the y coordinates at all these locations. So let's start at the origin, and at the origin the slope is 0, because y equals 0 there. So we'll get a horizontal tangent there. In similar fashion, as we move along the x-axis, the slopes continue to be 0. Now, as we move upward, at all these points, the slope will be 1 because y equals 1 there. So we'll plot slopes of 1. There we go. And as we move up to this row, all the y's are 2, so all the slopes will be 2. So we'll draw slopes that are steeper. And again, notice that I'm not looking for perfection here. I'm just drawing slopes that are steeper than 1 and look like about 2. Now let's go down here. Here all the y values are -1, so the slope will be -1, and I'll draw slopes of -1 there. And if we go down to the next row where y is -2, we'll get slopes of -2. And at this point we can probably sense visually what the curves look like. Looks like we have curves that go up to the right as you head northward, and also curves that head down to the right. And those look exponential, those families of curves. So we'll see if we get an exponential curve when we attack this algebraically. So let's try that. What I'm going to do now is move the y over to the left-hand side, and it will show up in the denominator as a 1 over y. And then I'm going to move dx up to the numerator on the right, so it's just a dx all by itself. And now that we've separated the variables, we've got the y's over here, the x's over there, we can now integrate. So I'll integrate both sides. When you integrate the left-hand side with y, you end up with the natural log of y. So we have ln of y equals, and when we integrate the right-hand side, what we're really integrating is 1. And when you integrate 1, you get x. And then I'm going to add a constant, which captures the constants that you get when you integrate both sides of the equation. Alright, now we want to solve this equation for y, so we're going to raise both sides using a base of e. On the left you get y, and on the right you get e to the x plus c1, which I am going to rewrite as e to the x times e to the c1. And remember that when you're multiplying expressions, you're adding their exponents. So we can equivalate, or we can make this the equivalent of that. And this expression right here has a numerical base and a numerical exponent. So this is simply a constant. And I'm going to call this new constant C2, and I'm going to move it to the front over here. So, to complete our work, y equals C2 e to the x. And that's our family of solutions. And notice that they are exponential curves. When c is positive, we're heading up to the right. When c is negative, we're heading down to the right. And we'll put a couple of points in there and see what those particular solutions would be. I'll just use a different color. Maybe I'll pick the point 0, 2 and the point 0, -1. And at 0, 2, our curve's going to head up to the right, and it's going to head down to the left. And in similar fashion, our point down here will send the curve down to the right and up to the left. So there are the two curves. And if we want to get their values algebraically, get their equations, we'll simply solve by substituting 0, 2 and 0, negative 1 into this equation over here. So I'm going to put in 0, 2, and when I put those in for y and x, we get that expression. So C2 is 2, which means that y is equal to 2e to the x. And that's the curve that's heading up to the right. I'll go over here to finish up my work. When I put 0, negative 1 back into this equation, I get negative 1 equals C2e to the 0. So C2 is negative 1, and y equals negative 1 e to the x. And that is precisely the equation for this curve.